Good day, my name is Nur Atika binti Doni with the matrix number 108358, and I will present the problem background and hydraulic assessment for the proposed Semulong Ulu gravity-fed water supply system. Currently, the village relies on an informal water collection system that becomes unreliable, particularly during the dry season when water demand is highest. The community consists of 3 longhouses supplied through 3 designated tap points located at different elevations. If the available pressure is too low, residents may experience insufficient water flow for basic daily activities such as cooking, cleaning, and personal hygiene. To address this issue, we evaluated a gravity-fed water supply system using a hilltop reservoir located at an elevation of 120 meters. The proposed network consists of a main pipeline that splits into 2 branches, supplying tap A, tap B, and tap C. Our first assessment was the static pressure audit. This analysis determines the maximum pressure in the system when water is not flowing. The highest pressure occurs at tap C because it is located at the lowest elevation, which is 70 meters above sea level. This represents the most critical location for pipe safety because excessive pressure could potentially cause pipe failure. Based on our calculations, the static pressure remains within the allowable pressure rating of the selected PVC pipes, indicating that the system can operate safely without risk of bursting. Next, we applied the extended Bernoulli equation to evaluate the pressure available when water is flowing under peak demand conditions. Using the head losses calculated from the Darcy-Weisbach analysis, we found that the delivery pressure at tap A is 195.3 kilopascals, at tap B is 325.5 kilopascals, and tap C is 432.4 kilopascals. Most importantly, even the most constrained tap point, which is tap A, still received approximately 195 kilopascals of pressure. This is significantly higher than the minimum required pressure of 20 kilopascals. Therefore, all 3 tap points are capable of supplying water adequately during simultaneous operation. These findings confirm that the proposed gravity-fed system is hydraulically feasible and capable of meeting the needs of the Semulong Ulu community.
Hi, my name is Nurul Ali binti Shamat. My metric number is 108448. For task 03, our team conducted a comprehensive hydraulic analysis for the Semulong Ulu gravity-fed water supply network. Our main objective was to mathematically verify that our chosen pipeline configuration can safely and efficiently deliver clean water from the reservoir at 120-meter elevation down to all 3 community tap points under peak demand conditions. To achieve an optimized and practical layout, we selected standard commercial PVC pipe dimensions, utilizing DN50 for the main line, DN40 for branch 2, and DN32 for branch 1 and the extension line. By applying the fluid continuity equation, our calculated flow velocities range beautifully between 0.497 meter per second and 0.637 meter per second. This is an excellent hydraulic result, as it sits well below the maximum erosive constraints of 2.5 meter per second, ensuring long-term pipe durability. Next, using the extended Bernoulli and Darcy-Weisbach equations, we evaluated the system's energy losses. As a result, our final delivery pressures successfully passed the project constraints. Tap A receives 195.32 kPa, Tap B receives 325.50 kPa, and Tap C receives 432.40 kPa, all comfortably exceeding the minimum 20 kPa requirement. In conclusion, this configuration guarantees an equitable, safe, and fully compliant water distribution network for the village.
Today, I'm going to present the final pipe network designed for the Semulong Ulu gravity-fed water supply system. My name is Yara Jane Chong Yarjun with the number matrix 108524. So, the final design uses commercially available PVC pipes consisting of a DN50 main line, a DN50 branch 2, and DN32 pipes for branch 1 and the extension branch to tap C. Starting from the reservoir, the main pipeline has a length of 350 meters and uses a DN50 pipe. Since this section carries the total flow from the reservoir to the junction, a large diameter was selected to reduce friction losses and maintain efficient flow conditions. The calculated velocity in the main line is 0.611 meters per second, with a head loss of 3.02 meters, both of which are within acceptable design limits. Now, moving on to branch 1. A DN32 pipe was selected over a length of 180 meters. The calculated velocity is 0.497 meters per second, while the head loss is 2.01 meters. As a result, Tap A receives a delivery pressure of 195.32 kilopascals, which is significantly higher than the minimum required pressure of 20 kilopascals. Now, moving on to branch 2, uses a DN40 pipe with a length of 120 meters. Hydraulic analysis produced a velocity of 0.637 meters per second and a head loss of only 0.23 meters. The larger diameter helps maintain adequate pressure further downstream in the network. Now, lastly, we will look at the extension branch to Tap C. The extension branch uses a DN32 pipe over a distance of 90 meters. The velocity remains at 0.497 meters per second with a head loss of 1.07 meters. This section delivers water to Tap C with a pressure of 432.4 kilopascals. Tap C is the lowest elevation point in the system and therefore experiences the high pressure. For this reason, a static pressure check was performed. The maximum static pressure at Tap C was calculated as 488.9 kilopascals, which remains below the allowable PVC pipe pressure limit of 600 kilopascals. Therefore, the selected pipe sizes can safely withstand the operating conditions without risk of structural failure. Beyond the technical requirements, this project addresses the challenges currently faced by the Semulong Ulu community due to inadequate water access. In highland villages, residents may need to spend significant time and effort obtaining water from alternative sources, particularly during periods of low supply. This can affect daily activities, reduce productivity, and make it more difficult to maintain proper hygiene practices. A reliable gravity-fed water supply reduces these burdens by providing consistent access to water at all designated tap points. By ensuring adequate pressure throughout the network, the proposed system supports better living conditions, improved sanitation, and more equitable water access for all households within the village. In conclusion, the proposed design satisfies all velocity, pressure, and structural safety requirements while remaining practical and cost-effective for rural implementation. To the panel, we respectfully recommend the adoption of this gravity-fed water supply system using DN50, DN40, and DN32 PVC pipelines, as it provides a safe, reliable, and sustainable solution for the long-term water needs of the Semulong Ulu community. Thank you.